All right, welcome back. More coding content. Um, Thanks for watching. If you're watching on YouTube, thanks for sticking around. If you're still on the stream, I think last time we did a bunch of. Actually, we finished converting the data to the frequency domain. So we're pretty much ready to wrap up the data, right? So we worked on data generation with Sionna, which is pretty much done. Remember, we started from this, let's do a quick recap. We started from the delay domain channels, which are matrices, but there's a delay and time component. Then we did the Fourier transform. Well, we used it in Sionna, right? Which moves us from the delay domain to this frequency domain. And we finally saw these very nice 2D plots of more complex channels. And these are really the 2D matrices we want to train a generative model, so the diffusion model on. And we also saved them to disk, but before that we have to fix a slight issue. What happens is in the future, we're going to want to ask for a lot of channels, right? For much larger channels, like maybe 64, 128. The problem is the computer may crash because internally this becomes a very large tensor. Remember, it's not only a 10,000 times 128 times 64. It's also times 2 dimensions, but actually it's times another internal dimension in Sionna because we kind of learned in the last episode, it's not the best software in the world, just from the packaging and from the way they do certain things. So today let's try to wrap it up with Sionna. So let's just chunk our data generation, and then off video or on stream, we computed this sort of max chunk size in the product. NumRx times NumTX times NumSamples is about 80,000. So here, for example, this product is gigantic, right? It's millions. So it has to be split into chunks such that NumSamples, the total chunk size is 80,000. Now we can only split the NumSamples axis. This is very important. We cannot split here. So let's do it this way. Let's add a parameter here. Now this will be different. It's also important that this is different for each computer because I happen to have a lot of RAM. So I can set this to 80,000, but it's gonna crash for users. Let me set it to 10,000. Okay, so it'll work for somebody that has 8 times less RAM than I do, and I have 128 gigabytes, so this is for 16 gigabytes. This is better, right? This is way more accommodating. Now there is a problem though. There's also a corner case. What if this is not even splittable? Because look here. So basically today we're gonna do a bunch of, let's say, data generation, but with hardware limitations, right? Because chunking is pretty common in AI, I think, for data loading or streaming and stuff like that. There's another corner case though. If I say that the max chunk product is this, but my dimensions, okay, they're almost there. What if I had here 128? I would be in big trouble because I can't even do one chunk. Okay, because it doesn't have, even if I do a single sample, I'm over the chunk prod. And there's no way around this. Like, if this means your computer will never be able to simulate not even one sample of this. So we're gonna have to issue a warning and attempt to continue in that case, but we want to give a warning to user. So we just gotta pay attention to all these special cases, right? So, because we want this toolbox, we want the paper or the repo to be friendly, and people to use it. I guess we can do a the diagram here would be pretty minimal, but this is basic data chunking, right? So it would look something like this. So ultimately, I want a data set. So what happens in Sionna internal is that it produces a tensor of size and R and T and time and frequency, and also has a really nasty N internal. Okay. I believe, if I'm not mistaken, N time is about 14 fixed for us, and N frequency is about 76. Okay. The problem is there's also this N internal that we saw, which is about 28 or something, which really blows up the data dimension, right? Because as a user, you don't care what happens on the inside. So you just want to specify B. What do you give? B, which is the number of samples, NR, and you also give it NT. Unfortunately, that doesn't mean the maximum array is that, because Sionna blows it up on the inside. So then what we're gonna do is we're gonna take this and we're going to split it into mini chunks, right? Which will have a chunk will have they're gonna have the same NR and Ts. We can't avoid that. Okay, so you cannot split on those axes. Otherwise, we would be able to split on a grid. But they'll have a B chunk, which is much smaller, possibly much smaller than B. Okay? Because we can't generate all the data at once. And NR and NT, they have to stay the same again. All right, so then we're gonna split this into multiple of these. Now we also need to be careful. The last chunk may be smaller, right? So B last chunk may actually be, it's gonna be the leftovers. So we're gonna have to do all those calculations. I wonder if there's some utilities to do those. Nah, we can just do them by hand. Okay, and then each time we're gonna call Sionna now with these. And this one will run, okay? So now instead of calling Sionna with the big one, which will crash the computer, we're just gonna call it repeatedly with the small ones. Whoops. Okay, and then we're just gonna do concatenation, right? So we're gonna call this splitting logic, okay? We're gonna write a tiny bit of code that splits, and it gives us, well, I don't even know how to draw these. It's fine. It gives us this chunk, and also this chunk, and also this chunk, okay? And then the only thing that we're missing is now so we're gonna have to down select the data, okay? Which we do today. So there's a small random sample the data, right? Oh, that's something else we did last time, I forgot. But we randomly subsample the data. And this gives us a single tensor, which is it's a 3D object now, so we're out of memory issue land. It's B chunk NR and T, and then guess what we're gonna do? Well, we're just gonna concatenate it, right? Now the last one will still be B last chunk because it may be smaller, and then we're just gonna do concat, and that's it. We're done for good. Obviously, right? Pretty basic. Just basic data manipulation. All these guys go together. Oh, we don't need this. There we go. Okay, I guess this is stuck now. And that's it. Then we finally get our data set, which is of the requested size. So the user doesn't even care about what happens on the inside, right? They'll just see magically B, NR, and T appear, but we have to split this way on the inside. And then with this, we can load it as training data for the model. That part is easy, all right? So this will go to this. And this goes to this. Okay, we're done. So let's quickly implement this. This should be pretty fast. Well, but the details are always slippery. Okay, so we can only afford a max chunk product of 128. So that means B chunk times numRx times numTx can only be that. We're also going to want a bar probably. So from TQDM import TQDM. Aha, we don't have TQDM in the Sionna group. What's happening here? We do not have TQDM. Okay, because we want to tell the user how far along data generation is. So for that, we're going to do UV add to the Sionna group, TQDM. I really hope this works. If it doesn't work, oh, it does work. Okay, so we added the Sionna dependency thanks to UV. Actually, again, I like to pin these down so it's exactly 67.3. And we should actually pin down the, now that I see it, we should pin Sionna no RT exactly to 121. Good, okay. So we pin down dependencies, we have TQDM, so we can show a progress bar. Where do we generate channels? Where's the num? Where's the batch size? Oh, come on. Oh, here it is. Okay, so we're gonna have to repeat this, right? So chunk the channel generation process. Okay, I messed up the logic. It's reversed. So I have to take this product and divide it by the size product. Okay, here it is. Finally, I got it now, I think. Okay, so this tells me that chunk size is gonna be 1 here, right? I think. Yeah, okay. Okay. So I can only fit 1 chunk. I mean, 1 sample in chunk, and the number of chunks is easy. It is just... this is the ceiling, right? So I take all the samples and just divide them by chunk size. Right, so then I'm gonna get 10,000 chunks here. Yep, okay. And for each one, I is 0. So then the samples in the first chunk should be 1. Yeah, and then it proceeds. Where the heck do I... Oh, I forgot one thing. Here's the mistake I did. I forgot to pass this. Huh. Okay, obviously we have to use this because we have to request these many chunks. Okay, we should be good now. Now this is still gonna take a while, but at least now we know this is a corner case where we have to split 1 sample. We can't fit 2 samples in a chunk. So we should see a bar with 10. Okay, we're pretty close. We got into storage. Random times. Be careful here. Again, we can't use num samples anywhere here. We have to switch to samples in chunk. Very important. Almost there. Yep, there it is. Okay, it's moving. So it's gonna take 1 hour. It's not too bad. At least the computer isn't crashing. Okay, and this is an extreme case where we can only fit 1. Now, what if we fit 2? Well, to fit 2, we just drop this down to 32, okay? So now we should see 5,000 chunks. Yep, there we go, 5,000 chunks. So we're doing 2 samples at once. Let's do something irregular. What if we have 4, 8? Okay, and the max chunk product is, what should we say here? 64, so I can do 2 samples at once, but I want 3 samples. What that means is the last chunk will be, I'll have 2 chunks, but the last one will be irregular, right? So then just to validate this, I'll stop here to see if the dataset size should always be what the user requests. There we go, 2 chunks, dataset shape, 3 samples, they're all populated, no zeros, nothing weird. Okay, good, we're done. So finally now we have a way to write data. This completes the CDL file for good. We should not touch this that much. Let me put these to some more human values. So I want, now we're gonna leave this 10,000, again, for users that don't have computers that powerful. Which I don't even know how this is gonna be, like what, 4, 8, like 300, so about 30 chunks for us here, right? Yeah, 33 chunks, okay. So let's just let it write this then, actually, because we're gonna need this data file, and we're done for good with this. We can finally now switch back here. Okay, it's done. Good. So we're done for good with that file. And let's see what we have here so we can commit everything. We added h5pi last time, and so git commit add h5pi dependency, and we just gotta commit the logic, add chunking logic to data gen. So now no more weird crashes. CDL. Okay, and the final thing we have to do is now we can finally go back to the, remember where we had to do this weird thing where we have 2 dependency groups that are incompatible with each other. Because the Sionna software is so bad, you can't even install it with NumPy, or you can bypass this, but UV, you can't get the log file. So now we can finally move back to Torch world. So we're gonna do UV run group torch -m MIMO dot, if I do train, okay, so now what we need to do is we need to go back to our data file, okay, and we need to import h5pi. So let me sync back my dependencies, group torch. Okay, so finally reinstall PyTorch. Oh no, okay. Well, this thing is working. I'm pretty sure I have h5pi here already. So then finally we can say something like this. Tag string or none is none. We're gonna need a tag for the data tool. And finally we're gonna say if this is CDL, so we're gonna do it like this. If CDL is in distribution, okay, then we're gonna extract the model, which I think we need some sort of basic regular expression. Well, actually, no, wait. We can just use this as is then, right? Because the convention will be CDL capital. Okay. So then we just need the file name. We want a mini error here. So if tag is none, we want to say raise value error. A tag must be specified when trying to load CDL data, okay? And this is cfg.tag, okay? So then we just need to form the file name. And there's also a data directory here, right? So data tag and data dir, path or none. So we want to import path. And again, we want to verify the same thing. So actually we can do this simpler. If config tag or it's data tag, right? So if data tag or config.datadir is none, a tag and folder must be specified because we want the user to tell us where to find that. And now we can just form the file name. And we're gonna have to mimic. This is not the best coding because we have to mimic the convention here. We'll have to figure out how to. I don't think there is a way though. You need a convention for data, right? I mean, you can't just let the user specify the file entirely. But it's the same thing because they would have to type it themselves. We'll think. Yeah, maybe it is better to. It's probably better to actually have users specify entire file names. Okay, so but anyways, so now we need to create the file convention. We know it ends in H5. What was the convention? Well, it starts with config.distribution, okay? So we're gonna want this to be, so now we can do a post init check here quickly. And we can say if config distribution, no, self, I mean, not in Gaussian CDLA CDLC or CDLD raise value error unsupported data distribution. Okay, so we can force this, which is also forced here, but it's fine. Double checking is not the worst. Okay, what else was the convention? Then underscore RX. This is sample size of 0. Okay, so RX is actually config.sample size 0. Then underscore TX. And then underscore tag. Was data tag, right? Okay, so we have the file name. Let's clean this up because it's expanding more often. Okay, so we have the file name, which is the full path, and then we're gonna say with h5py.file file name read. We need to import h5py. Got deleted again. Actually, these are all core Python. Okay. Well, not really. So we're gonna have to add to the group torch h5py. Apparently we don't have it, which is pretty wild. Okay, I'm gonna pin this down to 3.15.1. Okay, so now we have h5py installed too in this group, and as f, I forgot what the syntax was. Data is numpy as array. Oh, we need numpy here too. Okay. F at data. And finally, we're gonna have to convert to tensor. Data is torch tensor data. We're gonna shrink the D type down to torch complex 64. Because in PyTorch deep neural networks, they work on 32 bits. And that's it. Now we have a big ass. Okay, now the only problem is these sizes have to match now. So if we want to generate, let's generate 1664 data, 10,000 samples. Max jump product 10,000, although we know my computer can handle more. I think this is everything. Then now we can actually start the first training run on real data, which basically reproduces my grad school paper. Pretty wild. It didn't take too long. Almost. There's some details probably. So let's delete the data. So let's go through the full pipeline now, okay? So because of UV, we can seamlessly switch between dependencies now. We don't have to do anything. So we just do, first we have to generate data, okay? So, oh no, wait, we have to set the training up. So the data will be with tag. So data directory will be data, okay? Data tag will be train, okay? The model will leave by default. What else we need for data config? 1664 leave default. Oh, distribution. Let's do. Actually, let's change the default so it's CDLC, so it's easier. We don't have to mess around. So we just need the data dir and the data tag, which we specify data train. So then we want this guy to do C train data. Perfect. Is this a path? Yes, it is a path. So I'm gonna need a path to data. So I'm going to need from path lib import path. Okay, so now let's try the full pipeline. Anything else that I'm missing? So first we generate data, 1664 C10,000. 1664, this doesn't even need to know number of samples here. It just needs it for Gaussian, to be honest. So it's not important for CDLC. It's not used. And then this takes it here and loads it. And what does main do? It gets the data and it trains on it. That's it. Okay. So now the 3 full steps from scratch. So first we generate the data. UV run group Sionna -m MIMO.cdl. Okay, it's changing my environment dynamically, so we don't have to worry about anything. So it's basically ripping out everything and installing Sionna again, because it doesn't work together with modern Python, unfortunately. There is some overhead, but whatever. Okay, so we should see the chunked thing now. 10,000, 10,000. It's gonna take a while, probably. Right, 1664. Oh man, it's gonna be. Why is this so slow? What's happening? Oh, okay, it's because there is some overhead because I'm installing TensorFlow from scratch and it's initializing it the first time. Very annoying. Ideally, we just do this once. We're not really gonna. Okay, there it is. So it's 1,000 chunks. Okay, we're not gonna wait 8 minutes. Yeah, this is wild. Damn it. So let's just ask for fewer samples, like 1,000 samples. So this should be under a minute now. Now this doesn't have to be synchronized here, but I'm just gonna synchronize it, I guess. What is the batch size we use for training? 16. Okay, good. Whoops. Okay, I don't even know where I am here. Okay. So we're gonna run CDL again. We asked for fewer samples. I could ask for a bigger chunk size because my computer can do it. Okay, so this takes less than a minute to generate 100 data in chunks. And okay, this is done. Let's go. Okay, it's done. So now that's it. All we have to do is we can directly run the train. So UV run with the group torch -m MIMO.train. And by default, okay, I'll switch to packaging. Again, very annoying. I'll generate some data offline so we don't have to, we won't have to do this every time. But this should load the data, tensorize it, and train it with batch size 16. And we should really see the loss go down meaningfully now. Okay, that's it. It actually started. That's it. So it loaded the CDL. We're done, right? Let's see the training. Yep, there we go. Remember from the Gaussian, it was like, okay, this is the paper. It's actually literally the paper. Like, it's a crude version of it. There's many training details, but we're done with the data infrastructure. We're actually learning a generative model now on real, pretty complex wireless data, right? Because in the last episodes, we saw the CDL model is pretty complex. So yeah, this loss should eventually go down to lower values. Now we have to tweak the noise schedules. There's probably, oh, there we go. It's going significantly lower than the Gaussian, right? This should go down to lower values. We'll talk next time about what it means, what this loss means, what the noise means in more detail, and how to make it better, how to get the lower loss. And then finally, we'll be able to sample synthetic data. So that's it. Pretty good progress, very good progress. We're actually training a generative model. We're way more than halfway done, I would say. From here on, it's gonna get even more interesting. If you're into the AI side, we'll mostly focus back on AI now. So we're done with the data part. There will be a later part where we have to simulate the wireless channel, but we have a long way to go there. So thanks for watching, thanks for stopping by the stream, and I'll see you next time. Don't forget to subscribe to the channel if you like the videos, because I'll be posting regularly. Okay, training is going kind of haywire, but it's fine. Okay, bye.